Good afternoon. Welcome to the Baker Institute. My name is Regina Buono, and I'm the Fellow in Energy and the Environment here. And today we're having our third speaker in the Center for Energy Studies series on climate change and policy. This series will culminate in June with our final speaker. Mark your calendars, June 11th. And then the Center for Energy Studies will produce a paper on looking at what we've talked about over the course of the previous year. It's my pleasure today to introduce our speaker, Dr. Drew Shindell. Drew is a professor of climate science at the Nicholas School of the Environment at Duke University. Prior to joining Duke, he spent almost 20 years at the NASA Goddard Institute for Space Studies in New York City. He has testified on climate issues in front of both houses of Congress, in front of the UN's Climate Change Group, and in front of the World Bank. His research looks at global climate change, air quality, climate variability, and interactions with human society, all of which will factor into his talk today. We'll have a question and answer period afterward, so please hold your questions. We'll have microphones circulating. And with that, it is my pleasure to introduce Dr. Drew Shindell.
Good afternoon, everybody. Thank you, Regina, and the others from the Institute for inviting me out here. I wanted to talk today about climate change, but a little bit more broadly, the value of clean air. And I'm going to talk a little bit about some general thoughts about this issue to start and get into some more specifics later. And I'm looking forward to the questions at the end, so please do feel free to ask. I want to start by talking about the way we conceptualize emissions into our atmosphere. And I would hypothesize that most of you would agree with the way I tend to look at these, which is we look at these somewhat differently than we look at many other ways we affect our environment. And so if we have somewhere like this, a pleasant farmland or some nice region in the countryside or where our house is, and if we then see something like this, we'd not be very happy, right? To put it mildly. First of all, you might think that somebody should not be allowed to dump stuff on the land. This should be forbidden. Or if they do something like this, they should be made to clean it up. There should be a fine. And this is generally the way it works, right? If you are a business and you have to dump something in an approved area, you pay a disposal fee. If you dump something where you're not supposed to, you get in trouble for it, right? Nobody wants this on private land or public land. And we kind of feel the same about water. If there's somewhere, say, a lake up in the mountains where you go for vacation and, turns into something like this, again, that's typically forbidden by regulation, and there would be a fine. It tends to be a little less stringent. There's not typically, say, disposal fees the way there is for landfill. But this kind of stuff is also not really allowed. So what about you're driving along and you pass a factory, somewhere like this? We might think that the factory is not very aesthetic. What about that plume of smoke coming out into the atmosphere? Well, for one thing, after 100 meters or so, that's mostly gone away. So we might not be that excited to see such a thing, but do we really worry about it? We might think it's somebody else's problem. What about a more kind of immediate example? What about when you turn your car on? Everybody does this, right? All kinds of stuff comes out the exhaust, and we don't think that this should be forbidden or banned, or there's no fine associated. So why is it so different? If this was solid stuff coming out and it was spewing junk that landed all over the road or somebody else's driveway, we'd feel differently about it if it went in the water. Why is it the air? We treat it as kind of, well, just somewhere we can dump things. So there are a few reasons, one of which I was just alluding to a little bit. We have these different rules for solid waste, for liquid, and for gaseous. And one of those has to do with ownership, I think. All the land in the United States, for example, is clearly owned, right? Either by the federal government or by private citizens. So you have somebody who objects. Waterways are often owned, and if they're not owned, they're managed by the state or the government. So again, there's somebody that objects, but who owns the air? Nobody, really. Right? So there might be some regulations in some places for certain things, not for others. There's some things that haven't even been studied, but nobody owns it, and we tend to treat it as kind of, oh, well, it's just a universal place. We can let stuff go, not a big consequence. So is that really the case? I mean, I think if we think about it in detail, we'd realize that there are consequences, but I want to go over a couple of the consequences just to highlight these for you. One of the reasons that makes us pay less attention to this, I would say, the last point on this, is that we really do pay much more attention to things that happen in short time scales and that happen in one specific location. And that's not really the case with the air. So just kind of playing around and using my university's web resources, I decided to look at a few examples of this to see if I could support this hypothesis. One of the things I did was I looked up in the newspapers how much coverage there is in major newspapers for aircraft accidents versus auto or car accidents. So just a simple search, it took me a few minutes. About the same, right? So this is over a few-year period. When you have an accident, makes the news, people pay attention. Clearly, there are other ways to look at how much people pay attention, but it's about the same. So are the consequences about the same? I had to go for a longer period to find decent data, but aircraft accidents killed about 150 Americans during a decade. Motor vehicle accidents, more than 400,000. So why do we focus on the aircraft? Well, when an aircraft goes down, it's front page news, especially if it's a bigger plane, even if it's 20 people, because it happened in one time in one spot. And it's not really news if 100 people die on a given day in car crashes all across the country, and the next day 100 people again, and the next day 100 again. I mean, the very definition is news. It's not new if it happens every single day. So we just don't pay any attention to it, even though the consequences are far, far greater. So I think this is part of the idea that we really downplay things that are chronic. We kind of get bored of hearing about the same thing, and we downplay things that are diffuse. Now, if you think about what happens when stuff goes into the atmosphere, it causes climate change, it causes air quality degradation, and both of those happen over very, very big spatial scales and very long time scales, especially when you get to climate change. So these are two of the most broad chronic issues we face, and therefore it's really hard to make them into compelling issues that generate the same kind of response as, say, a big pile of trash on a pristine area of land. Stuff going into the atmosphere, yeah, it'll have an effect everywhere on the planet over many decades. Okay, now for the consequences. What does it do when stuff goes into the atmosphere? Why should we care? Well, we care about things like what goes in our body. Actually, a lot more air goes through your body every day than food or water. So that's one reason that it would be nice for that air to be clean. What happens when it's not clean? Well, this is the top 20 risk factors from the World Health Organization's Global Burden of Disease. So premature death due to various things that are avoidable. Two of those top 10, the two that are circled there in red, are air quality, poor indoor and poor outdoor air quality, respectively. The toll is about 8 million lives a year. In many places in the world, especially in developing countries, this is the single leading cause of premature death amongst women and children. And that's primarily, they are around cooking equipment. It's a bigger problem, certainly, in the developing world. We've had a lot of success reducing air pollution in the United States, but it's still a pretty big problem here, too. And so all of these areas that are in red, most of California and the eastern half of the country in orange or red, that's about 1 out of every 10 to 1 out of every 20 people that dies early is dying from poor air quality. So it would have been much worse in, say, 1975 or so. It's better, but it's not gone away here either. And of course, the toll is much higher in somewhere like China or India. Another thing poor air quality does is it stunts plant growth. So here's an example here, just growing wheat. with filtered air in the pot on the left and the ambient air in Pakistan, another place with pretty poor air quality. And so, this just makes it immediately apparent there's a huge impact here on your ability to grow food by having pollution in the atmosphere. And there was a study that just came out last year in the Proceedings of the National Academy, which estimated it up to a third loss of wheat and rice yield in India just due to their pollution. Now, this is a place where there are a lot of people who struggle to get access to adequate food. So this is tens of thousands of lives potentially in the balance, not from climate change in this case, but from the direct effects of the pollution. I'll talk more about how that interacts with climate change in a moment. So there are some good reasons to care about what we're dumping in the atmosphere, both from a standpoint of human health, standpoint of agriculture and our ability to grow food and food security, and of course, climate change. So this is a chart I don't really expect anybody to follow the details that hasn't seen this before, but this is from the most recent IPCC assessment, and it shows all the factors influencing climate change. The key point here is that this line represents 0, and anything on the left of that line is cooling the planet, and anything pushing to the right of that line is warming the planet. Unfortunately, most things are on the right, so we're getting warmer. The biggest one, the one up there on the top, is carbon dioxide. So obviously that is the elephant in the room when it comes to climate change. That's the single largest driver. There's no real uncertainty about this. But you can see that there are some other things that are pretty important too. And a couple of the ones that I want to highlight here are these: methane, carbon monoxide, and black carbon or soot. And so all of these both contribute to warming, right? And if you add those up, they're actually about the same magnitude as carbon dioxide, but they also degrade air quality, right? You breathe in soot, bad for you. Carbon monoxide and methane both create smog and ozone, which is, again, bad for you, bad for plants, etc. So these things are really tied together. The climate change and air pollution stories are really one story in my mind. There are some pollutants that are down there on the left as well, those, which are the cooling aerosols, things like sulfur. And so that's another reason why the stories get tied together, is if you try to think of actual policies, like, say, a change in how much energy you get from coal-fired power plants, you cannot do that without affecting the sulfur. Right? It's not as if there are magic wands you can wave that only affect carbon dioxide. The sources of carbon dioxide are, in almost every case, tied to the sources of all these other pollutants too. So one thing that's important is to treat these, in my opinion, together. I just want to highlight here that the uncertainties on something like the impact of carbon dioxide, it's shown by that little black bar up at the top, it's pretty small. Right. So there are things that we don't know, certainly about the climate system, in particular the particulates lower down that are circled, have some pretty large uncertainties, and how much they offset of the greenhouse gas effect. But when it comes to things like carbon dioxide, the uncertainties are really quite small. And it sort of stands to reason. The greenhouse properties of carbon dioxide were first measured in the lab in the 19th century. We've had a lot of time to work this out. So this is quite clear. And this will lead to, of course, impacts. So I've talked about some of the impacts from air quality. What are the impacts of the climate change caused by all of these different pollutants? Right? Well, one thing that happens that we are certainly concerned about is sea level rise. Anything that causes warming will cause sea level rise, and there are two components. One is just that warmer water expands. So any grade school science experiment, you can do that. And you take some water, you heat it up, it takes up more volume. So that part is extremely straightforward, almost no uncertainty there. We can measure that also, tide gauges, satellites, we see it going on. There's also melting of ice sheets, which can contribute to sea level rise. Those appear to be accelerating, but there really are very large uncertainties there in how quickly those will contribute to growth in sea level rise. So we can predict two components of this, one with very high accuracy, one with fairly low accuracy. But we know which direction this is going to go, undoubtedly. There are other consequences like more intense storms, including things like hurricanes. This is pretty much universally agreed because we understand the processes by which this happens. The storms get their energy from the surface ocean, and the surface ocean is getting warmer. That's, again, directly from measurements, from observations. You see it getting warmer, more power to drive the storms. More extreme precipitation, and this is a tricky one to communicate to people because when there's flooding and intense precipitation, we say this is the kind of thing we expect from climate change. And then when there are droughts, we say this is the kind of thing we expect from climate change. But last time you said it would be more water. Now how can there be less water? Well, actually there can be more of both. What we get is instead of having during a month, say 10 days with moderate rain, all the rain is piled into, say, 4 days. And so in between the periods of rain, you have more droughts, more dry spells, and when it does rain, it rains harder. And again, that comes from principles that really are pretty well understood. A warmer atmosphere has more water, more energy. It comes in more intense bursts when you have rainfall, but always tripping people up in communication. So you get both extremes, both floods and droughts pick up. These are kind of short-term events. You also get things like more heat waves, spread of tropical disease as say, mosquitoes can migrate to farther northern latitudes as it gets warmer. More wildfires. This is both from things like less rain going in, but also warmer temperatures causing more evaporation, leaving vegetation drier and drier. And in the western half of the United States, we're already seeing this playing out before our eyes. And with things like the wildfires, the change in snow cover, change in temperature, widespread extinctions, et cetera. The list actually goes on quite a bit longer than that, but I won't go through every particular example. One thing I did want to highlight, though, which relates to several of these points, is just how you can get so many of these examples being related to extremes. And so this curve shows the kind of thing that happens. You have a probability distribution where it's more likely to have, in this case, temperature in the mean, and you have some very cold days and very warm days. And that whole distribution shifts a little to the side. When it does that, the kind of average day likelihood doesn't really change that much. Right? It might be, say, 25% difference, 25% more, 25% less. But look out at the edge. You know, the days that were the hottest, the likelihood of those occurring might jump by, say, a factor of 5 or 10. And out at the record temperatures, things that never happened before now can happen. So the shift, it's not so much that it changes the average conditions. You know, we talk about things, the whole world is pretty much talking about 2 degrees as the target we want to avoid. 2 degrees doesn't really sound like that big a deal, and in many ways it's not. But a 2-degree shift in the mean corresponds to much, much larger changes out at the extremes. So for example, when you change climate by just a couple degrees, the heat wave that in France killed in the tens of thousands of people in 2003, that was estimated to be the kind of thing that would happen roughly once every 250 years under the climate of the pre-industrial. Now, or even the climate of the middle of the 20th century. By the end of the 21st century, if you increase warming by 2 to 3 degrees, that's kind of every other year. So that's when the likelihood is really changing by orders of magnitude, 100 times more likely, even though the mean temperature is only changed by 2 degrees. So that's why the impacts that I've talked about here, I focused on some of these extremes. Those can have the most consequence. Nonetheless, we often view things in terms of global mean because it's hard to make a graph of showing 47 different consequences out at the extremes. This is the kind of thing that is often used, 2100 temperatures. This is what the political negotiations tend to focus on, keeping warming at the year 2100 below 2 degrees. And you can see right now we're up at about 1 degree. The lower bars show some results from the mid-2000s, so 2005 or so slightly out of date by now. But if you just kept emissions where they were, if you had no emissions whatsoever, is that first one, then you wouldn't really change much from where you are today. People often get that confused with thinking that's keeping the emissions where they are. And keeping the emissions where they are is that bottom bar in the lower section. And keeping them where they are actually gets you probably 2 degrees, maybe a little bit warmer. In fact, since emissions have gone up over the last 10 years, we're now definitely farther to the right and past 2 degrees. So it's not just keeping emissions from growing in the future, it's actually bringing them down quite dramatically. And so the 4 scenarios up on the top are just denoted by numbers of how much impact there is from all the different pollutants. Those were the ones used by the IPCC. And you can see that there's a large range there. Each one, though, although it has a substantial uncertainty, which is the width of that bar, it's quite clear that they're distinct from one another, and it's distinct that on the path, say that upper one, the 8.5, the warming is vastly greater than 2 degrees, regardless of the uncertainty. There's a difference between 4 and 6, certainly, but 4 and 6, neither of those are anywhere near 2. Currently, we are on a path that most closely follows that 8.5, that upper scenario. So that's what we're trying to avoid, going to that kind of state where the planet warms by somewhere between 4 and 6 degrees. And unfortunately, we're not there yet. Currently, what do we do? Well, one of the things we've started to do in the United States is to try to bring our knowledge of the impacts into the policy world by putting a price on carbon. And at present, the Obama administration has done this via executive order so that federal agencies calculate the damages related to emissions of carbon dioxide, and they refer to this as the social cost of carbon. I have a quote there from the US government report on this, which is that it is intended to include, but not limited to, the kind of things we've been talking about. Changes in net agricultural productivity, changes in human health, property damages from things like storms and sea level rise, from increased flood risk, the value of ecosystem services due to climate change. So this is what we're trying to do in the United States to really bring this a little more to people's immediate attention, if you will, so that we don't say, oh, well, it just goes into the atmosphere and that's a global commons and it spreads out and there's no real consequence. Or maybe, well, 1 ton of carbon dioxide, what does that do, right? It's the whole planet is emitting it. It's a global problem. I don't really have a sense of what 1 single ton does. So the US government analysis puts a price on it, say $20 a ton. That's how much damage it does everywhere in the world, spread out due to our best understanding of what all these impacts are. Other parts of the world have somewhat similar methods. There's carbon trading now starting in parts of China, starting in California, and the European Union has an emissions trading system which is somewhat larger than the American system. It includes all the gases that are included under the UN's Kyoto Protocol. So this is also methane, which was on that chart, and some of the other things like industrial chemicals, hydrofluorocarbons, things like that. Now, what happens to air quality? That's not included here. As I mentioned, the same sources cause the same problem. And in the United States, air quality falls under either state or national rules, but is usually quite distinct from analyses of climate change. That's the same thing in Europe. The emissions trading system only includes the climate impacts of these gases and doesn't take into account that the sources generating those gases are also generating air quality. So in the US, if we have major legislation like the Clean Power Plant rule that's up right now, the EPA has of course done an analysis of the air quality impacts, but we don't have a simple way to do this for any given case. And one of the strange things about this, in my mind, there are several problems with this approach. One is that you see up above that what we're trying to include is the effect of these emissions on human health. Right? So if you emit a ton of methane and it causes the planet to warm and it causes tropical disease to move northward and more people die, that counts. If that same ton of methane causes more smog and people breathe it and die, that doesn't count. Because for some reason, we've arbitrarily separated climate effects from air quality effects. So I think that it's very difficult to justify including impacts based on the pathway by which they occur rather than the impact. I mean, we don't really care I would say, about the global mean temperature per se. It's not as if 2 degrees brings us to some ideal number, or even the current value is really right. We care about all these impacts, all the ones that we're trying to measure. But why care about how they occur? What we really want is the societal benefit of not having the damages from sea level rise and human health, et cetera. So that's one reason that I think that this approach can lead to inefficient choices. The other is that you can do things like China being extremely concerned now with their air quality situation. If you're only concerned with air quality and a different part of the government is worried about climate, as typically happens, then you might make a very different choice, like, well, let's just take our big polluting coal-fired power plant and move it to a remote area. And then we don't care. Nobody's out there breathing it, so we've solved the air quality problem, and that's all we care about. But now you've just built a brand new coal-fired power plant, which is going to generate CO2 for 80 years or however long that power plant lives. So you may have completely undermined your climate goals in order to meet your air quality goals. And these kind of trade-offs, I think, get lost with both the European and the current American system. What the European system uses to compare different pollutants is something called the global warming potential, which is an integrated measure of the radiative forcing. And in fact, this is not just the European system, this is the whole UNFCCC Kyoto Protocol. So what you do in that case is you sum the radiative forcing, which is how much the energy coming in versus going out of planet Earth has changed when you put a particular pollutant in the atmosphere. You sum that over 100 years. This shows these blue curves are the radiative forcing from CO2 on the upper one and the radiative forcing from methane in the lower one. Different pollutants have very different lifetimes. Methane doesn't stay in the atmosphere for very long at all, about a decade and it's gone. Carbon dioxide stays in the atmosphere for centuries. So you can see that the radiative forcing, you're summing over a lot of zeros as you go out to longer times in the case of methane, whereas the carbon dioxide is still contributing. The temperature response is shown in green, and that's the impact of this radiative forcing on climate change. And you can see that the curves, again, they have different shapes. So one of the problems with using something like global warming potential is that it doesn't really work to tell you what the temperature response will be. And in fact, when you calculate this, you find, it can be off by a quarter, it can be off by a factor of 2 for other pollutants. This gets to be very important when you're looking at something like the United States and our energy shift from coal to gas. Well, what we're doing is we're trading a very CO2-rich source for a more methane-rich source. So the comparison between these, being off by 25 to 50%, can have a big impact. The other thing that's very strange about this approach is that the social cost of carbon is an economic measure. And an economic measure uses discounting of the value of money as a function of time. And that kind of makes sense, right? $1 today could be invested, and 10 years down the road, you'd have more than $1, right? So in the business community, something like 5% discounting of the future value of money is typically used. In the study of intergenerational long-term economic impacts, often, say, the Stern report done by the UK government, they used a much lower value of, say, 1%. But that, again, is very inconsistent with saying what I'm going to do is sum over the first 100 years, and there's no discounting whatsoever. Every impact during the first 100 years has the exact same value, and every impact from year 101 on has no value whatsoever. It's wildly inconsistent, in fact, with any discounting, and no economist would ever use any sort of measure like that. So you can have values that are really hideously removed from kind of any logical consequence. So, in order to really inform policy, what I've been most interested recently is trying to form something that would give you a better way to really take account of the societal impacts of the various pollutants. And I want to give you one more example of why this is important. Radiative forcing is typically used. It was in that chart from the IPCC with all the little bars I showed. That tells you pretty well what the overall temperature impact will be. But again, looking at CO2 versus methane, thinking about, say, the trade between coal and natural gas, here's a look at the impact on agriculture. And this is kind of an interesting one, too. So the carbon dioxide is shown here, and carbon dioxide, by warming the planet, causes the rainfall patterns to change. In particular, some areas at lower latitudes tend to dry out quite a bit. You tend to get more rainfall in places like Siberia and northern Canada, where we don't grow very many crops. So the net impact from rainfall, as well as much warmer temperatures, which can kill off crops during the growing season, tends to cause a lot of damage. The unit here is kind of arbitrary. A lot of damage from the climate change. Heat and drought are the worst effects. But in the case of carbon dioxide, it not only changes the meteorology, the rainfall and the temperature that the plants are exposed to, but it changes the composition of the atmosphere. And plants like carbon dioxide. Plants take in carbon dioxide and use that. And that's part of what helps the plants grow. So that offsets a huge part of these damages, leading to a net value that's modest compared to the impacts due to climate change. Now let's look at if we trade carbon dioxide and instead have the same amount of climate change but driven by methane. Methane will cause, if it's driving the same amount of climate change, will cause the exact same change in your ability to grow crops by having more heat waves, droughts, etc. But methane, like CO2, changes the composition of the atmosphere, but not in the same way. Methane produces ozone, and those were the pictures I showed you before, the wheat in Pakistan. Ozone is not good for plants. It goes the other way. So ozone actually adds to the damages due to climate change. And then when you look at the net impact, you see there's about a factor of 5 difference. So a 2-degree world is in some ways a nice target, but a 2-degree world driven by methane is a very different thing than a 2-degree world driven by carbon dioxide. And it's much, much harder to grow food in a 2-degree world driven by methane. So there's really not simple to just say that the temperature change allows me to compare pollutants. They're really having different effects even on things like agricultural systems as well as on human health and other systems. Right? This can be especially important when you look at the World Health Organization analysis of what climate does to human health. Almost half of the impacts are due to increases in malnutrition. Right? So if you have a factor of 5 difference in your ability to grow crops, that's going to have an enormous effect on how many people are affected by climate change. So what I've been trying to do, and what I want to talk to you about a little bit in the last part of this talk, is develop kind of a social cost analog to what the US government uses, but something that's broader and has the same target, including all the effects we care about, human health, climate, et cetera. But it doesn't care about the pathway. They can happen via induced climate change, they can happen via induced air quality, and includes all the pollutants that cause both. Right? So even if something doesn't have a pronounced effect has only a small effect on climate or a small effect on air quality, if it affects one or the other, it's included. And so I can come up with values by using a model, the same way that the modeling has been done by looking at the impact of 1 ton of CO2. I do that with all the different pollutants, and we can then expand to include the climate impact beyond just CO2, and we can use a consistent way to value the effects. And so instead of the current case where sometimes the EPA will have done an analysis of the clean power plant rules and how they affect air quality, but somebody else will have done an analysis of how they affect CO2, and the methodology is not consistent and you can't really compare the numbers. This is one set of methodology applied to everything. And so I get something that's really not very interesting to look at, a table of numbers, right? But a table of numbers is very easy to use. So wouldn't pay that much attention to the values here. The point is that as a function, you can choose the discount rate to apply, and then you can calculate this for all of the different pollutants via all of their impacts. And then you take these numbers and you can use them to look at any given scenario, like what if I follow this emissions pathway? What if I choose these kind of standards for this particular source? And so let me show you a few of those kind of examples. Actually, sorry, before I show you a few of those examples, let me discuss a little bit about the uncertainty there, because it's hard to present the uncertainty in most of the examples. You just get overly complicated. So the uncertainty here is shown in relative to the mean, the median value for each of the pollutants. And you can see that there's a whole section down on the bottom where you have pollutants like ammonia, nitrogen oxides, sulfur dioxide. These have their biggest effect via air quality, not via climate change. And they have fairly symmetric uncertainties. And then you see some at the top, like carbon dioxide, and the third and fourth on the list, and nitrous oxide and HFCs. These have effects, these have almost no effect on air quality, but they have very large effects on climate change. And there the distributions are very skewed. And so the distributions become skewed because we don't understand climate sensitivity incredibly well. And what we do know about climate sensitivity is that the upper limit is quite a lot larger than the lower limit. So we have a best estimate, and it could be maybe about half that, but it could be several times larger. So that causes a skewness off towards the right. We also look at very long-term changes when we talk about climate change. So something like CO2 or nitrous oxide, these will be around for centuries. And so one of the things that becomes important then is how much money people have in the future. And so let me go to a little bit more detail. And if you look at the upper left there, that's the contribution of each potential source of uncertainty to the total uncertainty for carbon dioxide. And the largest one by far is projections in the growth of GDP. And so that's kind of an interesting case because, for one, we're not going to make that much smaller anytime soon. It's not as if we're suddenly going to figure out how to project what GDP will be around the world 100 years from now better than we can do now. We're kind of guessing. The other is that it's a really different sort of uncertainty because what happens is as climate change becomes stronger in the distant future, it lowers GDP, right? But you cause more damage if you're wealthy and you've built more stuff. So in some sense, this is not that we don't know how much damage will be caused by climate change, but we don't know how wealthy people will be, so how much they'll have to lose. And so by when that's far more positive, it's not necessarily such a bad thing. It's not saying climate is worse, it's saying it's causing more damage because we're more wealthy, so we have more to be damaged. A very different thing from some of the physical uncertainties. Some of the physical uncertainties are quite large, and the biggest one up there is that second from the top, which is the impact of climate change on human health. And that comes, a large part of that, as I mentioned before, about half of that is from malnutrition. Projecting malnutrition over time is another very challenging thing to do. How many people will there be in the future? How wealthy will people be, especially in developing countries? What will be their baseline health status? You know, how healthy will they be to tolerate having a little bit less food or need a little bit more food? These things cause a lot of uncertainty too. So when you try to include damages, it's not all just under our understanding of physical science. In fact, the main one for physical science is the climate response, TCR, transient climate response, the second from the bottom on the CO2 plot. And certainly understanding how much climate change you get for a given amount of pushing, right, from CO2 or something, that's certainly important, and that has that very skewed distribution, but it's not going to dominate in terms of the cost and the economic costs. It's going to dominate how much climate change actually takes place, but not how much value we place on that. And you can see that for the different pollutants, I won't go through all of these, and of course I'm not even showing all of them, but the contribution of the various factors can vary quite a lot. For something like in the upper right there, that's part of particulate matter with a diameter smaller than 2.5 microns that you breathe in, and it gets deep in the lungs and causes respiratory illness and cardiovascular disease and such. That effect in itself, the effect of composition on health, is by far the dominant source of uncertainty. Climate impacts are much weaker. Okay, so here are some of the analyses that come out when you use these kind of measures. This is the total cost in dollars for current emissions from the US electricity sector, and then subdivided into coal and gas, then the transportation sector, and then industrial combustion. And so you can figure out what they're doing to climate and air quality. It's a function of discount rate, and those are the first three bars, the blue, the green, and the yellow, with a higher discount rate, a smaller discount rate, giving more and more weight to the distant future. So the value goes up with time, or goes up with a lower discount rate. 5%, that blue bar, is kind of what business usually uses for near-term investment decisions. 3% in the green is kind of the median in the US government analysis. And the yellow 1.4% is roughly what was used in the British analysis in the Stern review. The red bar shows how much of that comes from air quality. So if you have a very high discount rate, then most of your damages are really coming from air quality, because the climate damages all take place so far down the road, you don't attach nearly as much value to them. If you instead have a very low discount rate, like the yellow bar, then you see it's much more of an even split. And when you look at the different sectors, something like coal versus gas, you see that coal, there's an enormous toll from air quality, whereas gas, it's almost invisible. You can hardly see the red bar. You can also see that even though the uncertainty range is pretty large, those black bars there that I just, to not make it too complicated, only included on one of them, it's a pretty big range due to all these possible sources of uncertainty, but nevertheless, the impact from, say, coal versus gas, extremely distinct. So you can really see the different damages caused by these. Transportation, air quality is one of the biggest effects to all the pollution that comes out of vehicles, with climate tending to be a smaller relative to, say, electricity. And the same thing for industry. It's the pollution that takes a bigger toll, unless you go to a very low discount rate. And I think that really kind of reflects society's, the real value society places on health. Human health, which is the only thing really affected by air quality, as agriculture as well. But that's tend to be affected by a lot more.
Is this for the U.S.?
This is only the United States, yes. Right. So if you want to divide this a little bit into, so this is, the total from coal and gas. It's kind of a strange comparison because we don't have the same amount of power coming from coal and gas. So it's a little bit of an odd way to do this particular analysis, and it's more useful to compare the different sectors and see where we might want to target our efforts. If you want to look very particularly at the electricity generation, then I think this is a more useful way to do it. Look at it in cents per kilowatt hour, and this just takes the Department of Energy's analysis of new capacity in the United States from last year or the year before, and how much it costs to generate electricity. So, the renewables have come down a lot from where they were, say, a decade ago, and they are now getting pretty comparable, but still, gas is the cheapest thing. And gas is substantially cheaper than coal or nuclear, so really this is no surprise when you see. It's no surprise to see what the U.S. has done over the last decade when you see a chart like this. Right? This is the cost somebody pays to build the plant and buy the fuel, and we've gone overwhelmingly towards gas because it's the cheapest thing on here. But what's really included, or what's really missing here? What's missing are all the associated impacts. And so if I take those values from that boring table I computed, and I figured out how much it costs, how much emissions are from each of these sources per kilowatt hour, how much impact they have and what it's worth, then I get a picture like that. Right? A very different story. Suddenly gas doesn't really look so cheap, and coal looks horrible. What I have are global numbers, so to make sure that these kind of have some resemblance to what you get in reality, and did some very, very detailed modeling for the United States, and then you get something like that. So actually they're a little bit larger. The United States is a pretty wealthy and populated country, so the impacts can be pretty big for air quality. Those go up a little bit, but it's not very different. So the point is, the market cost is quite different from the societal cost. Right? Now, what are these costs? Remember, there are things like sea level rise destroying infrastructure. People pay for that, right? We paid $60 billion for Hurricane Sandy cleanup, for example. That's not an imaginary cost. It's just not on the books for the energy companies or the vehicles or whoever really caused the storm to get more intense. The storm got more intense because of climate change, and sea level rise was higher from climate change. So when the storm came, there was more flooding because you started from a higher point. So a good portion of that is attributable to climate change, but the bill doesn't go there. Well, I showed you the impacts on the United States on deaths from air quality, for example, but it also sends over 100,000 people to the hospital every year with non-fatal heart attacks. Right? Somebody pays the medical bills. And so these costs here that are shown in the yellow or the orange, they're real costs to the market, but they're not associated with this particular source of the pollution. They're redistributed, so society pays the value that's shown by including those, but the electricity generation company doesn't pay that. If they're just generating power from natural gas, it costs them about 6 cents per kilowatt hour. Somebody else foots the bill for the rest. How can it be so large? So for something like coal, well, if you actually calculate the number of people killed by emissions from coal in the United States, it's a really big number. It's almost 50,000 a year, even though we've cleaned up a lot from where we were several decades ago. So we could, some of the cleanest power plants out there are not really very different from gas, but there's still some very polluting plants grandfathered in that emit a lot of stuff, and people breathe this, and so there's really, a very high toll, which gives you high valuation. The subsidies in the US, people talk about these. Why are we subsidizing fossil fuels? And this is, for coal, about $1 to $2 billion, about the same for natural gas. But the World Bank now is starting to refer to environmental damages which do not go on the books of those causing the damages as effective subsidies. If you look at those, these are orders and orders of magnitude larger. So there was an interesting discussion last month, 2 months ago, it's May now, where Secretary Kerry made these comments, and he said it's time to do real accounting. And the bottom line is that we can't only factor in the price of immediate energy needs, we have to include the long-term cost of carbon pollution. And we have to factor in the cost of survival. We'll have to stop government money from going towards non-renewable energy like coal and oil. Makes no sense to be subsidizing that. So I agree with most of the first part of the statement, but I think he's a little off on the targeting the subsidies. The subsidies are really, really quite small compared to the health costs, the insurance costs, and all of the other damages due to these. What we're not doing is really incorporating the true societal costs into the market. They're classic market externalities, which therefore there's no real incentive to clean up. Here's the last example. What about driving a vehicle? Right? This comes from some discussions with the U.S. Department of Transportation, which is working on improving electric vehicle infrastructure around the United States. And there's this question of, well, you've got to get the electricity from somewhere. So even though there's no emissions from the tailpipe of a car anymore, it doesn't even have a tailpipe, still there's pollution that's being generated from the electricity that's powering that electric car. So where does that come from? So from a typical gasoline car, about $2,000 a year in environmental damages due to the resulting climate change and air quality. From an electric vehicle, it depends, a pretty substantial dependence on where you get your power from. If you get it from coal, you're about a factor of 2 better. If you get it from natural gas, much better. And of course from renewables, then there isn't a lot of pollution at all. So it really does suggest how you can use these values to make these comparisons, which are then not just carbon dioxide. They're not even just direct emissions, but you can really tie things back to the indirect emissions that are related to the particular activity. Again, how can it be so large? $2,000 a year per car? Well, I think this is a really interesting example, and it goes back to this discussion that we had at the beginning, or the hypothesis I made that we pay attention to sudden local events. So you probably all remember the story of GM and the faulty ignition switches. This was big news in congressional hearings. They recalled millions of cars. So it was a huge effect on their business as well. I've seen news stories since I made this slide, and I think some people claim maybe up to 20 deaths over a decade rather than 13. But it's kind of ambiguous. Anyway, let's say it's 10 to 25. It's somewhere in there. What happened to what was the cause or the consequence of the emissions from GM cars over that same decade due to air quality? Well, you can work that out. It's about 40,000 people. So even though we have a congressional hearing and we force them to recall their cars when there's a faulty ignition switch, When the cars are operating as they're supposed to and pouring out pollution out the back, nobody says, oh, they should be taken to court. Oh, they should recall these. These cars are killing people, right? Because it's not a clear thing. You know, you have a simple example when somebody was going around a turn and their ignition switch failed, they hit a tree, right? Cause and effect are very clear. It happened at one spot to one person. We know exactly who did it. It's very clear to link the damage to the root cause. It's not so clear when somebody dies from a heart attack. Why do they have a heart attack, right? Statistically, you can go through the medical studies and you find that air pollution is causing over 100,000 people to die every year in the United States from heart attacks. But you don't think, oh, this person died from a heart attack because of a car or a power plant or whatever it was that caused the pollution. Now, we don't tend to think that way because it's a statistical relationship rather than, you know, a direct link that makes that so clear. So I think we've come to grips with this for something like smoking, that it's a statistical relationship, and people understand that when somebody dies from lung cancer, that's not a natural thing if they were a smoker. People don't really have the same thought that when somebody dies from, you know, cardiovascular disease, often that's not a natural thing either. So I think that kind of brings back to where we started. There's a part of this is the way we think about the problems, about diffuse chronic problems, and so I think that's one of the nice things about really attaching a price, which is the way that most of the world seems to be going, incorporating carbon markets, incorporating pollution trading, and I think that's really something that makes it clearer. Everybody knows what it means to say that it costs $50 a ton to emit carbon dioxide. Nobody really knows what it means when it says it causes 0.0001 watts per meter squared of forcing. And so this really brings it home. Once we have those values, I think we need to incorporate them either directly into the market and then let the market find its way to deal with them, or we need to do things like put in place regulations so that society doesn't get stuck with the bill for these costs, which are market externalities currently. I think as I was mentioning, they help societal understanding, and I think by providing a metric that is easy to use, I'm hopeful that this will allow people to really evaluate choices in the United States as China tries to clean up their pollution, as we try to improve vehicle efficiency standards, renewable portfolios, et cetera. We can really see which are the best strategies to follow. So thank you again for having me, and I look forward to some questions.
We are having tremendous number of tornadoes. What do you think is causing that?
Sorry, could you say that again?
Tornadoes in the Midwest lately. What do you think is causing that?
Oh, is it what's likely to be causing that? So tornadoes are, climate change. We usually try to understand by both looking at the processes and seeing if we can understand the drivers. Like for hurricanes, when I was saying it, they feed off the ocean warmth, and we try to look at models and see if the models could reproduce them. And if there's multiple things that all point in the same direction, then we can understand them a little bit better. When it comes to things like tornado outbreaks, they're very small scale phenomenon, and models tend to not be able to capture those well. So we don't have that line of evidence. We have some basic physical understanding of how they're formed from energy within the atmosphere. And a warmer planet and more water vapor in the atmosphere does contribute to making those more readily formed and more powerful. So there's, I would say, fairly weak evidence that those might be linked to climate change, but it's not kind of the observations, theory, and modeling that we like to have to really conclude anything strong. So I'm afraid that one's still somewhat equivocal.
When you looked at premature deaths, did you look at the number of years associated with the premature death? You know, if you're 19 years old and you die in a car wreck because of the braking system, it's terrible, you lose a lot of life. But if you're dying of a heart attack at 77 rather than 80, I was just curious, is that something that went into your calculation?
Yeah, so we did do some analyses of that, and the medical community really prefers that metric because it does capture just what you're talking about, and they like disability adjusted life years is their preferred way of looking at these things, because even if you don't die, a disability can profoundly affect your well-being. The problem with that is that the economists don't like that. So it's easy to calculate the years of life lost or the disability adjusted life years, and I have both of those, but it is not easy to put a dollar value on that. And the reason is that economists have various ways of assessing how much it's worth if somebody dies early, like looking at what they call revealed preference, and you have one job and then a very similar job but a higher death rate, say working on a tall skyscraper and maybe falling off, versus construction jobs that are on the ground. How much do people have to be paid extra to take that job? And that tells you what kind of the market values a life. When you look at something like a child dying or an elderly person dying, the market doesn't put a value on those. So it's kind of, it's unfortunate, but if somebody's not contributing to the economy, oh, well, they were retired, so they're worth nothing. And so you get stuck between the medical community and the economics community. So we calculated them for the sake of knowing what's going on. And in particular, the pollution is worse, has stronger impacts on children and the elderly. So it actually looks worse when you look at years of life lost than when you look at total number of deaths. But I don't know how to put a price on it.
As an economist, just to follow up on that issue, lately there have been a couple of publications in the very top economics journals where they've tried to value things like the value of all research done by NIH. And so some of the very top economists have been forced to put a value. So I think you could use those and you wouldn't get any complaints from economists. And sort of, at $100,000 per quality just of life year comes to mind. So I can send you the sites for those. I appreciated your model. I thought it definitely looks like the logical way to go to include all the different involved. One thing I'm wondering is consumers get consumer welfare out of cheaper energy. So lower taxes on gas and coal and things like that. And I'm pretty sure that there would have been economists who would have calculated the dead weight loss from higher taxes or things, which would be the policy intervention to try and reduce, some of the use of these things. And I'm wondering if that consumer welfare is added in as sort of an offset to, some of the costs you're saying that are resulting from use of these various different fuels.
Right. So thank you for the initial comments on the valuation. For the latter comments, I think, let me see, now I've suddenly...
It's just that we're actually, it's sort of, yes, there's a cost to all these,
right.
all the
But the welfare.
Pollution produced by the cars, but we're also getting a lot of consumer utility value out of driving those cars around and,
right.
All that. So it's sort of, it's the value current consumers receive from using up all this energy.
Yeah,
and,
okay. So I think that, you can get to some very illogical conclusions if you take some of these costs too far. Like you look at the value of agriculture in the United States, and as one of our sectors of the economy, it's quite small. So you can really eliminate all agriculture, and it doesn't do very much to GDP, but obviously it would do a lot in practice if we had no food. And so really these are useful for most useful, I think, for examining trade-offs, like between different sources of electricity, rather than say, oh, we don't want to have electricity. So if you look at the benefits, people would still want to be mobile. So it wouldn't be get rid of gasoline vehicles and not have a replacement. It would be, what if you swap gas to electric? Or what if you swap renewables, for fossil fuels for electricity? And then there's certainly, if I understood correctly, you're alluding to there is this kind of welfare also that goes on to the poorer people. And if you put a tax on some of these, you get to interesting equity issues where, right, we have a gas tax right now that's only like 20 cents a gallon or something. Really, if you look at the costs I've calculated, the environmental damages are more like $4 a gallon. But if you put $4 a gallon onto price, then for people that are low income, how would they afford to get around anymore? Right, so that you would need to, I think, be quite careful to ensure that different groups don't lose the welfare that they have now, and energy or mobility doesn't become unaffordable. I think you could do that by the way we currently subsidize, say, heat for low-income people. You take however these costs are incorporated into the market and you make sure that that's redistributed to ensure welfare. But that's another really important criteria if you ever want to put these into practice. Yeah.
Dr. Shindell, thank you for your presentation. Very interesting things to think about. My question is on the premature deaths and some of the numbers that we saw in your presentations. I often, part of my job is to follow some of the regulatory and regulations that are out there. I often see deaths associated with these regulations that are cited in these regulations. Right. And these statistical deaths, I have a hard time sometimes when you add these statistical deaths up in all these regulations. You would have 10% of the U.S. population falling dead today if you add up all these regulations. I mean, that doesn't happen in real life. How do you reconcile what's statistical deaths with actual deaths? I don't ever see anybody go back and reconciling that and saying, did those deaths actually take place? Or are they just economic and statistical deaths?
Well, no, I think the numbers I was citing for things like the non-fatal heart attacks and the deaths, those really they do seem to correspond to what really goes on. But it can be, it's very difficult to validate the exact total, because when people die from, say, cardiovascular disease, right, how do you really know if they died from cardiovascular disease because of air pollution or not? So I think getting a definitive number is unclear, but you have some very nice studies that go in addition to the statistical relationships, where you just get kind of a regression between exposure and response, and you have cases. There are a couple. I don't want to take too long, but a couple that are really interesting examples is a valley where there was a big smelter, which was the dominant source of pollution, and the employees went on strike. And so if you had 1 year where it was in effect a randomized experiment, everybody that lived in that town, their exposure dropped precipitously for 1 year, and then everybody had the exposure go back up the next year. And so you can really see how many people, what the medical toll was. And China, there's a really interesting case too, where there's a river about the middle in latitude across China, and north of the river they subsidized or gave out coal for home heating, and south of the river they didn't. So hundreds of millions of people on each side, basically from all walks of life, but one exposed to more coal pollution than the other, and about 5 years of life lost for everybody north of the river compared to everybody south. So I think you have some really clear-cut evidence that the pollution really does kill quite a lot of people.
Thank you for a very illuminating talk. One of the challenges is of comparing the effects of CO2 and methane is how you value the impacts over time. And you showed an application of different discount rates, which tend to put more emphasis on what happens sooner, largely the methane effects, then discounts things that happen in the future. One of the counter arguments is that the methane, by happening sooner, it's causing warming when we're not at catastrophic levels of warming, but the CO2, the warming that happens from the CO2 could be later when we're already at 2 or 3 or 4 degrees warming. So did your analysis account for what increment that amount of warming was being applied to, whether it was already at a higher level, and more broadly, things get complicated for decision makers when you're showing them 5 different levels, 5 different discount rates, and looking at this might make it more complicated. What do you think is the best way, if you had to have some way of, on one single metric, comparing things, what would be the best way to account for things over time?
Yeah, thank you. So the damages that accrue due to climate change are in the analysis I did, which is really following one of the main assessment models used in the US from Bill Nordhaus up at Yale. The damages then are a function of the square of the temperature. So yes, as you get into the future where you're already warmed, then a slight increment has much greater value than a slight increment now. So the discounting is pushing the value down in the future, whereas the baseline warming is pushing it up in the future. So those are competing against one another, and why you don't have even stronger divergence across discount rates. But I used the US government rates because I wanted it to be comparable to what was in our current policy. They use constant rates of 5%, 3%, and 2.5%. What I actually think is the most sensible is there's never going to be a right answer to that. It's somewhat of an ethical question. It's not a science question. But I think a fairly large discount rate initially, something like the business world, because that's what society is already using. But then a rate that declines over time is what I would prefer, rather than a constant. So I did some of that in the analysis, the published analysis. It's not comparable with what the U.S. government uses, but I think that that's useful because it's the tail. If you have a 5% discount rate all of the time, then there's almost no effect out in the future. So if you look at the uncertainty, and if you go from 5 to 1, all of the valuation out in the tail and the long time scales comes from the low values. So in order to really include that uncertainty, even if you start high, you should have it taper with time so that you don't neglect the distant future. And then you still argue about exactly the rate that it tapers, but you've much better characterized the spread across all possible or plausible discount rates if you have one that declines with time. So that's what I favor, definitely. So in order to, it's a hard question because in some sense it implies that there is a particular point at which you cross from okay to not okay. And so really, to avoid the kind of impacts I was talking about, we should have acted a long time ago. And so we are committed already to a fair bit of warming, to sea level rise, to extinctions, to a bunch of things are going to happen. But the degree to which we experience these impacts is still very much under our control. And it's a very, I think that we have very, very little chance at this point of hitting 2 degrees. The only scenarios that hit 2 degrees have negative emissions for the whole planet starting in several decades from now. So this is over a period of several decades when we project energy demand, for example, to double as people in the developing world rise out of poverty and into the middle class. This is providing a huge amount more energy while we're growing at 2 to 3% a year in emissions. It's not just bringing that to zero. It's not even bringing it down. It's going actually negative, which is pulling carbon out of the air, which we don't actually know how to do, or carbon capture and sequestration on thousands of power plants everywhere around the world, even though so far it's working on one. These are things that are almost unimaginable. So I don't think we have almost any chance, unless Paris this December is phenomenally successful beyond almost anybody's expectations of meeting 2, but it's a really, really different thing to be at 6 than 2.5. And so we need to, the quicker we act, the better chance we'll have of being towards the low end. Right now, as I was saying, we're on that upper end path. And so we are aiming towards around 4 to 6. And that will be awful. The consequences will be horrible if we don't get off that path. But how the longer we wait, the harder it is to really get down towards the lower end. So I think within the next, if emissions don't peak by 2020, 25, something like that, and really start to get down quickly, then we're up towards the upper end with 3, 4, 5 degrees, and then the damages will be pretty horrible.
So 5 to 10 years is like critical.
I would say so. I mean, people have been saying that for a while now. We really have to act immediately, but they were kind of right, and I think we have closed the window on some of the lowest ends. Many of the small island states were asking that the worldwide target not be 2C, because that will probably put them underwater, but it be 1.5. And I think we missed that. We didn't act when people said, you have to act now or we're going to not make the target. It's too late. So I would say it again, even though it sounds like I'm just repeating it, but yes, I think the next decade, there has to be a big change, or we're starting to commit ourselves to the upper end.
Yeah, I want to thank you for what I consider a fairly remarkably honest presentation, where you acknowledge a lot of uncertainty. I was just wondering, who is trying to use this work as a jumping off point for additional work? I mean, I can imagine some examples of an economist saying, oh, could we create a cap and trade program or a tax that includes all sorts of pollution, or even having Tesla take your work and say, hey, it looks like electric cars look better even if you use coal power. But who's using this work to go forward?
Well, at the moment, so this paper that documents all of this just came out earlier this spring. So it hasn't been put into practice anywhere as of yet, but hopefully that will change soon. One of the groups I've talked to, as Regina mentioned in her introduction, is the World Bank. And the World Bank does a lot of funding, of course, of development around the world. And their current president is trying to make climate change one of their key issues. So they are trying to do things like include better climate evaluation when they consider projects, whether it's road building, hydropower, et cetera. And so one of the things, when you see this kind of work, you see, for example, there's a good value to controlling methane. And the value is larger than you would expect if you only thought of, say, what's under the Kyoto, the radiative forcing impact, and you disregarded the agricultural impacts and the health impacts from the ozone. And so the World Bank has a couple programs. One is that to provide the capital to municipalities around the world to put landfill capture, gas capture. And that's a really nice program, because a lot of times you put these capture facilities on these big municipal waste dumps, right? Landfills generate methane. You capture it, and it pays for itself, usually in the range of like 3 to 6 years. But just because it pays for itself doesn't mean, Kanpur in India has the capital to put it in place. So the World Bank doesn't take that much money because they get paid back for it, but they can give that upfront capital that, in the US we might have, or Sweden or somewhere, but is not available in many places where there are currently no regulations. They get paid back, they use the money to fund it in another place. Gas flaring, they have a big initiative to reduce gas flaring from the oil industry. That's another one that I think, again, will easily pay for itself. So there are some things you can do that are really economically pretty attractive, and it doesn't take a huge amount of money to get a large impact. But these really help highlight where to steer that money. Another is diesel retrofits of vehicles, bus fleets in developing countries. Typically, there's huge diesel bus fleets pouring out all kinds of stuff, and they don't necessarily have the money to put filters on these vehicles or buy new electric buses. So those kind of things, the World Bank, there's a group called the Climate and Clean Air Coalition, which is really it's about 40 countries trying to get together to catalyze action on things that both improve air quality and mitigate climate change simultaneously. So I've got a lot of buy-in trying to get these things going, and those are the ones that are so far interested in these kind of metrics.
Audience question, but I'm going to go a little bit rogue and ask you if you are going to attend the climate talks in Paris, and if you have any predictions on what might come out of that, and then we'll wrap it up.
Sure. I am planning to attend, and I attended the last as well. It's, my projection here is that we will have some fairly impressive sounding commitments, and it will be quite some time before we really see how they pan out. For example, one of the main developments was last year's U.S.-China agreement. And that was really, in many ways, a big step. But it was a big step in that China came on board after, in previous UN negotiations, saying, it should be the developed world to go first, and we don't want any rules. But it's also difficult to know what it means, because what they committed to was having their emissions peak in around 2030. But we don't even know how much they'll peak at. They could continue to soar until 2030, which is a very different thing than kind of not changing very much from what they are now and then going down. So for the whole world to really turn around and bring its emissions down, we're going to fail miserably to do that if Chinese emissions keep going on the trajectory they've been on. So I think we'll get something that'll sound nice, and I think the politicians feel compelled to offer some successful sounding thing at the end, but it may take us many years to really figure out what we've got.
Great. Go ahead.
I think I should talk for a while. If you put carbon capture and storage into your economic equations, do you get some of this money back, or do you get enough back to say that it's more economically feasible to do that than to go on the way we are? And if so, how about geoengineering?
So if you put carbon capture and storage in, then certainly you offset all of the emissions from a carbon, and it's worth something. The problems I have with carbon capture and storage is the engineering type studies, which is not my work, but other people's work that show you need something like a network of pipelines that's as big as what we have now for oil and gas. And that took over a century. So if, for one, we haven't really demonstrated that that works at a commercial scale. The first plant using that just opened in Canada a matter of months ago. But what we need is to have that on almost every plant in the world. And we need to have this huge network to transport it from those plants that are not located in places where it's geologically suitable to store the carbon and capture and storage. So I think it can play a small role if we're lucky and all the technology and the costs turn out to be good. But I can't see it really getting us to where we want to be. It's just too much of an engineering task to put in place quickly enough. So for geoengineering, I think that there are some obvious appeal to that. But it's somewhat of the problems like I was alluding to when I compared carbon dioxide to methane. And you can tune, in some sense, the planet's temperature, the way you could get, particular reduction in global mean. But that doesn't mean that all of the other responses are exactly the same. And so what I was showing with the agriculture was 2 degrees from CO2 is not quite the same thing as 2 degrees from methane, because there are a bunch of different effects that happen. And so if you have 4 degrees from CO2 and then you offset 2 of it with geoengineering, so you're back down to 2 degrees, that's not necessarily the same thing as just having hit 2 degrees in the first place, because whatever geoengineering effect you put in will have different effects than the CO2 that you're trying to offset. In particular, most every geoengineering scenario involves putting particles, reflective particles in the atmosphere. And so you change the balance between how much sunlight comes in and how much energy goes out in the infrared. And that will change where it rains, and that will change how you can grow crops because of the sunlight. So you might get the temperature where you want it and still not have managed to remove all of the other damages due to the warming. So I think that's one of the key problems. The other is governance, and how you could ever manage to get the world to agree. As soon as you start geoengineering and the rainfall shifts from one country to another, what is the country that now has drought for the next several decades because everybody else needs the benefit from the geoengineering, and that it prompts lots of potential for conflict, and who's going to control which amount of geoengineering, where should it be done, how much should it be done, what if there are winners and losers, who compensates the losers, and we have enough trouble working out something, a deal on things that we don't know, things that we know much more about. At least we have evidence from the last 100 years of what happens when you put CO2 in the atmosphere, and we're still having trouble working out a deal on how to limit that. But we don't have any evidence of exactly what happens if you deliberately geoengineer the planet. And so then who gets to make the decisions? I find it almost inconceivable you could have a worldwide agreement on that.
We do need to make that the last question. But I want to thank you all for coming, and I want to thank Dr. Shindell for a very interesting talk, and we hope we'll see you in June.